Hello everyone, we're going to talk about section 5.4. So this is going to be on annuities, present values, and amortization. So we already talked about annuities, but we talked about annuities with future values. So now we're going to talk about annuities with present values. So in the annuities that we studied last section, we make regular deposits that were made into interest-bearing accounts that begin at zero and then they end in a larger amount. So that's the future value. So we calculate the accumulation of funds into an interest-bearing account. Now we're going to include annuities that begin with an amount and make regular payments until the value of the annuity reaches $0. So this is the paying out funds concept that we mentioned in the last section. So in the last section we mentioned that there were two different types of annuities, and that's either we filter money into an interest-bearing account, and that is the accumulation of money or future funds, or now we're doing out the paying out funds. So we have an account that starts with a balance and we're making regular payments on that balance until the balance reaches zero. And the paying out funds gives us this following equation. So we have if x is a non-zero real number and n is a positive integer, then we get, and then that final equation there is 1 minus x to the negative n power divided by x minus 1. So all you really need to know about this equation is that it's going to help us create our present value equation. Just like in the last section, we had a similar looking equation, and that helped us find our future value equation. So getting into present value, in section 5.2, we said the present value is the amount that must be deposited that day in order to produce $a in n periods. But in this section, the present value of an annuity is the amount that must be deposited that day to provide all the payments for the term of annuity. So we're saying that if we have to pay off a certain amount, we have to deposit a certain amount today so that in n periods of time, we would have paid off that debt, making our regular payments. So our equation for a present value of an ordinary annuity is the present value P of an ordinary annuity is given by P is equal to R times 1 minus 1 plus I to the negative n power divided by I, where R is the payment at the end of each period, I is the interest rate per period, and n is the number of periods. We also have that second equation there, but we're not going to really bother with that equation very much. We're going to stick with the long one, essentially. All right, so let's do present value problem. So we have example 1 here, which is also number 2 in your book. We want to find the present value of the ordinary annuity. So we have payments of $890 made each year for 16 years at 6% compounded annually. So all we need to do is use this equation. So let's figure out what's what in this case. So we know our payments are going to be $890, so we're going to have R is equal to 890. We're making them each year for 16 years, and it's being compounded annually. So our interest rate in this case, since it's 6% annually, we get I is equal to technically 0.06 divided by 1, since it's annually, but since we know that that's just equal to 0.06, that's what we're going to write. I is equal to 0.06. And since it's annually, every year for 16 years, our n value is just going to be 16. All right, so we have all of our parts now to our present value equation, so let's fill it all in. So our present value equation we know is going to be P is equal to R times 1 minus 1 plus I, the negative n power divided by I. So when we fill this in, we get 890 times 1 minus 1 plus 0.06 to the negative 16 power divided by 0.06. So we can simplify this just a little bit. So we can simplify what's in the parentheses there. This gives us 890 times 1 minus 1.06 to the negative 16th divided by 0.06. So I strongly encourage you to take a moment and calculate this value on your own. And if you had, you should have gotten $8,994.25. So this means that if we want to pay $809 each year for 16 years, and this value is compounding annually at 6%, our present value, or the value that we need to put into our account in the very beginning, is going to be $8,994.25. Now, just a word of caution, you don't ever want to confuse the formula for the present value with the, of an annuity with the future value of an annuity. So I wrote the equations again there, and you can definitely see they are very similar. The only real difference is the numerator, where in the case of the present value, we have 1 minus 1 plus I to the negative n power, and in the numerator of the future value equation, we have 1 plus I to the n power minus 1. It's very important not to confuse those two formulas, because you'll just be solving for a completely different thing. All right, so number 2 here, we want to find the payment made by the ordinary annuity with the given present value. So in this case, we're given the present value, and now we need to find the payment. So in this case, we're solving for R. So we have $90,000. We have monthly payments for 22 years, and the interest rate is 4.9% compounded monthly. So we know our equation we can just rewrite is P is equal to R times 1 minus 1 plus I to the negative n power divided by I. So I know that that's our equation. Doesn't really look good now. Here we go. We know that's our equation. We know we're needing to find our monthly payments. So the values that we do have are P is equal to 90,000. We're trying to find R. We have an interest rate at 4.9%. It's being compounded monthly, so remember we need to divide by 12. That'll be 12 periods in 1 year. And then our n value, remember, is the number of periods in our entire duration of time. So compounding monthly for 22 years, we're going to get n is equal to 12 times 22. And n will be equal to 264. And I can plug all of this back into our equation and solve for R. So we get 90,000 is equal to R times 1 minus 1 plus, I'm going to scooch this down a little bit here, a little bit more room. We're going to get 1 minus 1 plus 0.049 divided by 12 to the negative 264th power. And then we're going to divide by that 0.0449 divided by 12. All right, so we have this entire equation. Now what we really want to do is we want to calculate this value inside of our brackets. So our brackets here, we want to calculate that value first so that we just have some value multiplying by R, so then we can just divide by that value and get our value of R. So I invite you to calculate this on your own. And if you do, you should get 161.38 times R. So now all we need to do is divide each side by 161.38. This gives us R is equal to $557.68. So we know to pay off $90,000 in monthly payments for 22 years at an interest rate of 4.9%, our payments are going to have to be $557.68. All right. Moving on to example 3 here. We want to find the lump sum. Oh, example 3 is also number 15 in your book. We want to find the lump sum deposited today that's going to yield the same total amount as payments of $10,000 at the end of each year for 15 years at the given interest rate of 3% compounded annually. All right, so this is a multi-layered problem. So the first thing we're going to do is that we need to calculate the future value of our given information. So we want to know how much is going to be at the end of 15 years. So first, we want to calculate the future value of our information. All right, so our future value equation is S is equal to R times 1 plus I, that's an I, to the n power minus 1 divided by I. So remember, this is our equation. So let's plug our values in. Right here, let's first label what our values are. So we know R is going to be $10,000, or just 10,000. I is 3% compounded annually. So I is just going to be 3%. And we're thinking about 15 years, and since we're compounding annually, n is just going to equal 15. All right, so let's calculate our future value. We get S is equal to 10,000 times 1 plus 0.03 to the 15th power minus 1 divided by I. So now that we have this value, as always, I encourage you to pause the video and calculate this on your own. And we should get that our future value is $185,989.14. So we know that our $10,000 at the end of each year for 15 years, or our $10,000 just at the end of 15 years at a interest rate of 3% compounded annually is going to become $185,989.14. All right, mouthful there. So now we need to find a lump sum that's deposited today that's going to be equal to this contribution. And we need to contribute an amount that's equal to this present value. So we need to use all the same information and calculate our present value. So now we want calculate present value. All right. So now we want to calculate our present value in order to find our lump sum. All right, so we're going to use all the same values here. We know our equation, so let's plug everything in. So we know our present value is going to be equal to R times 1 minus 1 plus 0.03 to the negative n power, so negative 15, divided by 0.03. Oh, I wrote R. So let's fill that in with 10,000. There we go. So we have our equation. So let's calculate this value. And you should end up getting $119,379.35. So the lump sum we need to deposit today is going to yield the same total amount as payments of $10,000 at the end of each year, 15 years, at our given interest rate, which was 3%, is going to be $119,379.35. So now, if we want to check if our answer is correct, we want to use our compound interest formula. So we can use compound interest formula to check. And our compound interest formula, remember, was just our value of P times 1 plus I to the value of N. So if we plug these values in, we're going to use our P value, our present value, so $119,379.35 times 1 plus our interest rate to the value of N, which is 15. If you calculate this value, you should end up getting $185,984.14. So now we've checked to make sure that this value was correct. So we know that our future value of $10,000 at the end of 15 years at a rate of 3% would give us $185,989. Sorry, this is a 9, not a 4. $989.14. Then we calculate our present value, and then to check to see if our present value was correct, we just used our compound interest formula to see if it would end up with the same amount of money at the end of 15 years. All right, so just a blurb from the book here, we have the present value of an annuity for accumulating funds is the single deposit that would have been made today to produce the future value of the annuity, assuming that the same interest rate and period of time. So this is basically saying that our present value of a single deposit into account that's made today is going to have the same future value of the annuity. So that's why we were able to calculate our future value and then calculate our present value. And then once we figured out what our present value would be in the same amount of time, it was the same value. All right. So we also learned about corporate bonds in section 5.1, and we see that the interest rates when a bond is sold differs from the interest rate paid by the bond, and this is known as a coupon rate. So this is basically just telling us the interest rates when the bond is sold versus the interest rate when you pay the bond. And these are going to be different. This is the coupon rate. So we're going to do a problem of the coupon rate. So this is going to be example 4, which is a combination of example 5 and 2.5. So we have a 15-year, $10,000 bond with a 15% coupon rate, was issued 5 years ago and is now being sold. If the current interest rate is 7%, what price should a purchaser be willing to pay for the bond? And then also, what if the current interest rate is 4%? So we're going to be doing this twice with 2 different interest rates. So, first things first, we want to calculate the simple interest rate. So we want to calculate the simple interest rate paid by the bond each half year. We are essentially going to treat this bond as a two-part investment. So we need to calculate it for the half years first. So if we want to calculate simple interest, which we know is just I is equal to P times R times T, we have I is equal to 10,000 times 5% times half a year, 1/2, so 0.5. And when we calculate this value, we should get $250. This is the interest that we're making on our bond every half year. So, like we said before, we're going to consider the bond a two-part investment. So we'd say the first part is going to be an annuity that pays $250 every 6 months for 10 years. All right, so the first part is just going to be the annuity that pays $250 every 6 months for 10 years. So what we've been doing. Now the second part is going to be the face value of our $10,000 bond, which will end up being paid when the bond matures after 10 years. All right, so we know that the first part is going to act as this annuity, so we're going to be paying the $250 every 6 months for 10 years. But the second part is the face value of the bond. So if we're investing at $10,000 and we're essentially waiting 10 years, or compounding every 6 months in this case, for 10 years, that bond is going to increase in value. So you need to be paying your investment or paying into your annuity at the same time the bond is maturing and also gaining value. So if we want to do our first part here, I'm going to label this as 1 as our first part. So we'll say first part is 1, our second part is 2. So our first part here is we're finding the present value. We already know our equation, but in this case, we know R is going to be $250. I is going to be, since we're saying that our now current interest is going to be 7%, then we know I is going to be 0.07 every 6 months, so technically semi-annually, so twice a year. And our N is going to be twice a year for 10 years, so 20. So I can plug everything into our equation. So we get P is equal to R, or we already know our equation. So R is 250 times 1 minus 0.07 divided by 2, sorry, 1 plus that, 1 plus 0.07 divided by 2 to the negative n power, so to the negative 20th power. Then we're going to divide by I, so we have 0.07 divided by 2. All right, so we found our equation. As always, I invite you to calculate this value on your own. And you should get $3,553.10. So we're going to say our present value is $3,553.10. And we want to find our face value of our $10,000 in 10 years. So, come on. Here. So this present value that we saw for in the first, this is present value of an annuity. Find our face value of $10,000 in 10 years. We're just going to calculate the present value of $10,000 in 10 years. So this is using our equation of present value that we used before this section. And if you remember, that present value was P is equal to A, or our future value, or ending amount, of 1 plus I to the negative n power. So that was that equation. So now we're going to plug everything in. So we know what we want to solve for P. Our A value is our $10,000. We have I plus 0.07 divided by 2 to the negative 20th power. Now, if you'd like to calculate this on your own, you should end up getting that P is equal to $5,025.66. So after 10 years, our present value is going to be $5,025.66. All right, so now if we're saying that our purchaser, or we're asking our question in our thing here, we're asking what price should our purchaser be willing to pay for the bond? So our purchaser should be willing to pay the sum of the two present values. Present. So they should be willing to pay $3,553.10 in addition to $5,025.66. So we're saying that the purchaser should be willing to spend $8,578.76. All right, so we calculated our value at a current interest rate of 7%. Now we also want to know what if the current interest rate was 4% instead of 7%? And we definitely ran out of room, so we're gonna pull the rest of our question over here. We're going to ask, what about 4%? Because what we saw here was that initial interest on our $10,000 bond was 5%. So the bank bought the bond at a 5% coupon rate, and now it has interest that is different, and this is going to be the interest paid by the purchaser. So if we're thinking about what about 4%, we're going to do the same thing as we did before, except now we're working with 4% instead of 7%. And we still know our value, our monthly payments are still being made at $250, so we're just going to do the exact same thing. The only change is the interest rate. So we have now the interest rate is 0.04 divided by 2. So we're still doing that semi-annually. So same things. We're going to do that first part, which is our present value of annuity. And then we have 2 here, which is our present value of $10,000 in 10 years. All right, so calculating our present value of annuity, if we want to do the same thing, we know P is equal to R, which is $250, times 1 minus 1 plus 0.04 divided by 2 to the negative 20 power divided by 0.04 divided by 2. And if you calculate this on your own, you should end up getting that P is going to be equal to $4,087.86. Now remember, we're going to do the present value of $10,000 in 10 years. So we're going to do that same equation that we had before, which we had P is equal to A times 1 plus I to the negative N. So we know that P is equal to 10,000 times 1 plus 0.04 divided by 2 to the negative 20th power. And if you calculate this value, you should get that P is equal to $6,729.71. Now we know that our purchaser is going to have to pay both of these sums, so let's add them up. So the purchaser should pay both of the two present values. So we just add them up, so we have $4,087.86 plus $6,729.71. And after adding these up, we should end up getting $10,817.07. So we can definitely kind of see a commonality in these two cases. So we can say here right below we have our note. So we say if interest rates rise, then our bond prices are going to fall. So our bonds are going to be worth less if our interest rates rise. Then if our interest rates fall, our bond prices rise. So our bond prices will gain money, or they'll be more expensive if our interest rates end up falling. All right, so now we're going to move on to loans and amortization. So if you take out a car loan, you repay it by making regular payments to the bank. If the bank sees this action that you're doing and making these regular payments for your car loan, your bank sees this as being an annuity that's paying a fixed amount each month. And the present value of this annuity is the amount that you borrowed. So the original amount, let's say maybe you borrowed $10,000 on a car loan, and you're making regular monthly payments on it. Your present value of that annuity is just the amount that you originally borrowed. So that present amount is going to be $20,000. A loan is amortized if both the principal and the interest are paid by a sequence of equal periodic payments. So your loan will be amortized. This just means that if you're paying your equal periodic payments on your loan, so you're paying both the principal and the interest, because you're not just paying $20,000 back every month. That $20,000 is gaining interest, so every time you pay per month, you need to be paying the interest plus the principal. So we have our amortization payment. So we know a loan of P dollars at interest rate I per period may be amortized in N equal periodic payments of R dollars made at the end of each period. So this is the end of each period. We're paying at the end of the period. So this means that we end up with our equation of R is equal to P divided by 1 minus 1 plus I to the negative n power divided by I, or in simpler terms, P times I, or principal times our interest rate, divided by 1 minus 1 plus our interest rate to the power of negative n. So once again, our amortization payments here that we're trying to find, this is the same exact equation that we had for our present value of annuity. Our equation is just it's been manipulated. So now we're solving for R instead of solving for P. All right, for example 5 here, we want to find the payment necessary to amortize the loan. And we have $2,500 with 8% compounded quarterly and 6 quarterly payments. So this is technically about 1.5 years if we're doing quarterly payments. So this will be 4 payments in 1 year plus 2, so that's about 1.5 years. So we use our equation here, which we know is going to be R is equal to P times I divided by 1 minus 1 plus I to the negative n power. So we want to find our R value. We know our P value is 2,500. Our interest rate is 8% quarterly, so divided by 4. And then we have our N, so we have 6 quarterly payments. So if you were saying quarterly for 1.5 years, 1.5 times 4, so it's still 6. Since we're saying that we're doing this for 6 quarterly payments, our N value will be equal to 6. All right, so now we just want to plug all these values into our equation. So we get R is equal to 2,500 times 0.08 divided by 4 divided by 1 minus 1 plus 0.08 divided by 4 to the negative 6th power. And I invite you to calculate this value on your own. And if you do, you should end up getting that R is going to be equal to $446.31. So these are the payments that we'll need to make every quarter in order to amortize the loan. So we're paying off our principal and we're also paying off our interest. That's why it's not $250. Take a moment. $2,500 or $2,500. Why it's not going to split equally among 6. See, we're paying the principal and the interest, so it's going to be more than an even split. So just because equal payments are made to amortize a loan doesn't mean that the loan balance will decrease in equal steps. And this is because a significant amount of each payment just pays the interest. So you're not going to be paying the exact same amount every single time. You're going to be paying based on the interest that you had gained. So now we have an equation here to calculate our remaining balance. So if a loan can be amortized by n payments of R dollars, each at an interest rate of I per period, then the approximate remaining balance B after X payments is B is equal to R times 1 minus 1 plus I to the negative power of n minus X divided by I. So we're looking at basically the same present value. The only thing that really changed is now we have a value of n minus X. So we know that our remaining balance will be however many periods that we had to pay minus however many payments remaining. So this helps us create an amortization schedule. So to determine the exact amount remaining after each payment, financial institutions use the amortization schedule. So it lists how much of each payment is interest, how much reduces the balance, and how much is owed after each payment. So included here, we have an example of an amortization schedule. So we see here that at payment number 0, this is our initial value. So this is going to be our present value. So your initial part here is $1,000. Then we see that our interest rate in this case is just going to be 10%, 1%. So we see here that the amount of our payment in this case is going to be $88.85. Then our interest for the period is going to be $10. So $10 is going to be taken out over $88.85 since that was the interest you gained that period. So the portion that you're actually paying towards your principal is going to be $78.85. So that's why your principal at the end of the period is $921.15. So the amount that you're paying every month is going to be about $88.85, except for that very last month, which is $88.84. Because of the amortization schedules, we want to make them as equal as possible in the amount of time that we have. But we see here that a chunk is always going to be paying the interest, and then the rest will be paying the principal. So it's going to take longer than if you were cutting everything into equal steps. All right, for example 6 here, we have Susie borrows $2,500 for 2 years at a 9% annual interest compounded quarterly. So we want to find her quarterly payment, and then we also want to find, after making 6 payments, she decides to pay off the remaining balance. Approximately how much should she pay? So if we're thinking that after making 6 payments, she thinks, oh, okay, I have enough money to just pay off the entire rest of the bill, she's going to save money since that amount isn't going to be making that interest. So she'll be saving money, but it's going to be one lump sum to finish off the loan. So for part A, we know that our p-value is going to be, and I realized that I wrote a number wrong. I must have had 2,500 stuck in my head from the last problem that we had. So it's supposed to be 3,500. There we go. All right. So it's $3,500 for 2 years. So our p-value is going to be 3,500. We're paying quarterly for 2 years, so 4 times 2. So n is going to be 8. And our interest rate is 9% divided by 4. So if we just want to find her quarterly payment, we need to use the equation that we just learned in our last little part there. So we want to learn R is equal to P times I. So I'm going to bring that down one. So 3,500 times I, which is 0.09 divided by 4, divided by 1 minus 1 plus 0.09 divided by 4 to the negative n power, so negative 8. So I invite you to calculate this value on your own. And you should end up getting that R is going to be about $482.95. So your quarterly payments should be about $482.95. But after making 6 of these payments, she just wants to pay off her remaining balance. So how much is she going to pay? We're going to use our equation here. So, our equation is B is equal to R times 1 minus 1 plus I to the negative n minus x, all divided by I. So if we plug our values in here, we have R, which is 482.95, times 1 minus 1 plus 0.09 divided by 4 to the negative n minus x. So our n value was 8. We made 6 payments, so it's 8 minus 6. So we want to find whatever is remaining. And then we're going to divide by our interest rates, 0.09 divided by 4. So we know that this value here is just going to be equal to negative 2. So I invite you to calculate this value on your own. And you should get that your balance remaining is $934.25. So Susie's going to save some of her money by paying off those last 2 payments basically all at once. And $934.25 would be her remaining balance if she had already made 6 payments. All right, so now we're going to talk about annuities due. So we want to find the present value of an annuity due in a certain amount of payments of our dollars at the beginning of the period. So what we just talked about was paying our certain amounts of payments of our dollars, and this is going to be at the end of the period. So now we're going to do the beginning of the period. So the first payment always earns no interest, but every payment after that does, forming an ordinary annuity. So our very first installment doesn't earn interest, but every installment after that earns interest. So what we basically have to do is we have very similar equation to the equations that we've been seeing. It's just that now we have our initial payment plus a similar version of the equation that we've been seeing. And then our n value is just going to be n minus 1 since that very first payment didn't earn interest. So putting this all together, we have the present value of an annuity due, and the present value P of an annuity due is given by P is equal to R, which is our one payment, our first payment, plus R times 1 minus 1 plus I to the negative n minus 1 power divided by I. And this is our present value of an ordinary annuity of n minus 1 payments. So this is basically saying that our first payment earns no interest, but every payment after that will. So we have our first payment plus every payment after that. And we know that R is the payment at the beginning of the period, I is the interest rate of the period, and N is the number of periods. So for example 7 here, we want to find the cash value of the lottery jackpot to the nearest dollar. Yearly jackpot payments begin immediately, so 30 for the Powerball. Assume the lottery can invest at the given interest rate. So if we have the Powerball and it's $57.6 million, 5.1 interest, we want to find the cash value of this. So this meaning we want to find our present value at this very moment. So I believe this is normally because if you win the lottery, in the case of probably the Powerball, you have the option of taking the installments for 30 years, or you have the option of just taking the cash value when you win. So it's having either one very large lump sum immediately or still large amounts of money for every installment after that. So that's what we're comparing here. So our Powerball, which is 57.6 million, we are going to rewrite this because we don't really want to write 5, 7, 6, and then all the zeros that come after this. So we're going to rewrite 57.6 million as 5.76 times 10 to the 7th power. So this is our scientific notation. All right, and then we're going to see what our equal payments would be. So we're just going to take our 57.6 million and divide it by 30 because you would get that amount for 30 years. So that's a completely even amount that we're distributing. No interest or anything like that. So we want to see, we want equal payments for 30 years. So we would end up getting just 5.76 times 10 to the 7th power, and we're going to divide that by 30. And you should end up getting 1.92 times 10 to the 6th power, which is also like saying $1,920,000. So we found what our equal payments would be for 30 years. Now, we want to find its immediate cash value. So we're going to use this present value of an annuity deal. So we found what our equal payments would be. So 1.92 times 10 to the 6th power. So this is that first payment plus our normal payments times 1 minus 1 plus 0.051 since it's yearly. And then we have negative 30 because it's 30 yearly payments minus 1 since our first payment gained no interest. And then we're going to divide by our interest. So now we have this equation. And let's just simplify it a little bit. So we get 1.92 times 10 to the 6th power plus 1.92 times 10 to the 6th power times 1 minus, this is 1.051 to the negative 29th power divided by 0.051. So now we want to calculate this value on our own. So I invite you to calculate this value. And if you do, you should end up getting about $30,669,881. So that would be your cash value of the lottery jackpot. So we definitely see that's a lot different than $57.6 million. So when you have the option of taking the immediate face value or the cash value of the lottery versus an installment for 30 years, in this case for the Powerball, taking the investment of 30 years would definitely be in your best interest. Because if you take the cash value of it, it would end up being $30,669,881. So you see that's about $27 million less. All right, so that finishes up our section 5.4. So this one was definitely a little on the long side. So if you have any questions at all, of course, never hesitate to email me, pop into my office hours, submit an anonymous question into the anonymous question form, or anything along those lines. Let me get my thing up here. So don't forget those options are available to you at any time, and I will see you all virtually later.